The so-called standard interpretation of quantum mechanics is that we separate out the measurement process as being something different and use our simple rules to work out the probabilities of various outcomes. For engineering, this presents no apparent problems as long as it keeps working for every problem we ask it to solve. From a scientific or philosophical point of view, however, it's very unsatisfactory for at least two reasons. First, we still apparently have no description of how the measurement process works. Second, we have no idea at what point we make the boundary between the quantum mechanical world and the presumably macroscopic world of measurements. The quantum system evolves in superposition states until we measure it, but we don't know what measurement is. Our normal classical view of reality is that we have a determinate experience of things being in specific states rather than superpositions. The standard interpretation is an example of a theory in which reality, in that sense, is created by the act of observation or measurement, whatever that is.
The classic illustration of the absurdity of the standard interpretation is Schrödinger's cat. Here's Schrödinger's cat. And Schrödinger imagines that he puts his cat in a box. And he also puts in the box an atom. And a bottle of poison. The atom can decay radioactively, a random quantum mechanical process, which may or may not occur. If it occurs, it triggers the release of poison gas from the bottle, killing the cat. But if we cannot see inside the box, what is the state of the cat? Is it alive or dead? If a quantum mechanical state only collapses when it's observed, what we could call observer-created reality, then the cat should be in a linear superposition of alive and dead. Until we open the box and observe one state or the other, and in this case, of course, the cat is happily alive. Schrödinger argues that superposition is absurd for a cat. Whether it's absurd or not, and whether absurdity should be given any weight in deciding the validity of a quantum theory, provided the theory agrees with experiment, are both matters of opinion.
The Copenhagen interpretation is essentially due to Bohr. We know that we must accept wave-particle duality. Entities such as electrons have both wave and particle character. Such a duality requires us to accept two views that, in a classical approach at least, are contradictory, or in the terminology of the Copenhagen interpretation, complementary. We also note that certain variables, such as position and momentum, have a complementarity to them. We can accurately only know one of these at a time, as given by the uncertainty principle. Then, perhaps, we should extend this complementarity principle to other aspects of quantum mechanics that are also apparently contradictory. For example, we might say we have a complementarity between the linear superposition aspects of quantum mechanical states, which have character also seen in waves with their linear superposition, and the apparent definite states seen as a result of measurements. Those measurements have a kind of character seen also in particles with their definite discrete existence. Modern opinion is sometimes that generations of physicists were misled into believing that Bohr had solved the problem of the interpretation of quantum mechanics, including the measurement problem, though no one was precisely sure exactly how he had done this. For example, the famous physicist Murray Gell-Mann said, and I quote, "The fact that an adequate philosophical presentation has been so long delayed is no doubt caused by the fact that Niels Bohr brainwashed a whole generation of theorists into thinking that the job was done 50 years ago." Whatever Bohr was advocating is not clearly defined mathematically once we go beyond aspects like the uncertainty principle and wave-particle duality. And it does not appear to offer a way of resolving the difficulties of the interpretation of quantum mechanics. A common problem with the Copenhagen interpretation is that one cannot find a consistent or clear definition in the literature as to what it actually is. Another view was advanced by David Bohm. This work was in some ways an extension of an idea proposed by Louis de Broglie, an idea called a pilot wave. In this approach, the quantum mechanical wave is regarded not so much as giving the state of the quantum mechanical system, but as giving a wave that somehow guides the particle in what is actually a deterministic motion. Bohm noticed a particularly interesting analogy and extension of a particular approach to classical mechanics. His extension of this approach allowed exactly this kind of pilot wave interpretation, at least for the simple Schrödinger equation for an electron. In this view, the randomness comes from our ignorance of the precise starting conditions of the electron, which is allowed to have well-defined position and momentum. This is not itself a contradiction of the mathematics behind the uncertainty principle, which is telling us relations between attributes of the quantum mechanical waves. In Bohm's pilot wave approach, that wave does not itself determine the precise position or the momentum of the particle. To see how this works, we can re-examine Schrödinger's equation.
We start with the time-dependent Schrödinger equation. So here it is, the same as we've seen before. And then we make a mathematical choice to write the wave function as the product of two terms here. A function r, capital R, of the position, vector r and time, and an exponential of I times s, which is another function of vector position r and of time. And r and s are real quantities. Well, we can always choose to write any complex function in this kind of form. This is the real amplitude, as it were, of the function, and this here gives us the phase of the function. If we substitute this form into Schrödinger's equation here, then after some algebra we can deduce this equation, where q here is del squared, the Laplacian, of that real function r, the amplitude, divided by r, and multiplied by minus h bar squared over 2m. Well, this equation here, but without this term, which we'll call the quantum potential, so an equation in this form, is known as the Hamilton-Jacobi equation of classical mechanics. It reproduces the usual classical behavior of a particle. S is then called the action, or Hamilton's principal function, and the momentum is the gradient of that action. So that's ordinary classical mechanics, just written a slightly different way. This equation is a completely deterministic equation, in which position and momentum are both simultaneously well defined. For a large wave packet and a large mass, then the quantum potential, Q, would be a very small correction. And hence, even using the full form with this Q added in, that we had looked at before, for such effectively classical situations, we would simply obtain the familiar classical behavior.
Bohm's assertion, then, is that because we can use definite position and momentum as meaningful concepts in the classical version of the Hamilton-Jacobi equation, we can also use them that way when we add in a finite quantum potential Q. Here, we have a potential Q derived from the solution to Schrödinger's equation. We are merely adding in the potential from that other field to the Hamilton-Jacobi equation, just as we might add in another potential from, say, an electromagnetic field that's a solution of Maxwell's equations. This quantum potential also acts together with the other potentials in the system to guide the particle. As a result, this potential, or the wave function that generates it, can be regarded as a pilot wave. As far as Schrödinger's equation is concerned, there's nothing apparently wrong with Bohm's assertion. The randomness of quantum mechanics in this picture comes from the ordinary randomness of the initial positions and momenta of the particles. This picture does correctly reproduce the results of classic experiments like diffraction through two slits. The wave function, through the quantum potential it creates, gives the necessary additional potential to guide the particles, one by one. An ensemble of them, with suitable random starting conditions, will reproduce the diffraction pattern we see. It will have zeros at specific points as required. If we block a slit, we block the wave function from passing through that slit. If we do that, the wave function will not have a two-slit diffraction pattern. Hence, neither will the quantum potential. Hence, the ensemble of particles will not show a two-slit diffraction pattern either, just as we expect. Note, though, that in this picture, the particle does definitely go through one slit or the other, and any individual particle does have definite position and momentum at all times. Because of this definiteness, there is no collapse of the wave function required to explain definite measurements. There have been many objections to this picture. In this simple form as presented here, it's not relativistically correct, and it only applies to one particle. Approaches to addressing such problems do exist, however. It does also appear to give a special status to position, whereas the conventional description of quantum mechanics treats position on an equal footing with any other dynamical variable. The measurement problem is based on the linearity of quantum mechanics. Perhaps quantum mechanics is not actually exactly linear. Perhaps the effects of that nonlinearity become strong as we move to the macroscopic world in which we appear to exist. Then we could discount the kind of proof we gave above and propose that some state collapse is possible. This approach does not seem to get a lot of attention, presumably because no one's been able to come up with a theory that both satisfactorily explains the microscopic world and yet gives the kind of state collapse we think we see. Perhaps the process of measurement and the collapse of the wave function occurs when a conscious mind, whatever that is, intervenes. Consciousness then lies outside quantum mechanics as stated so far. Such a supposition might allow us to test experimentally for the presence of consciousness in a chain of events. Consciousness would presumably collapse the wave function and lead to behavior after that time that was different from the behavior we would have seen for a true superposition. If the system that is supposed to be conscious is a relatively complex one, such as a human brain, it's doubtful we could calculate the time evolution of a true superposition in interacting with that system. So we likely could not distinguish it from the time evolution of a collapsed state of a complex system. Hence, this experiment is perhaps discouragingly hard. Also, having no clear definition of consciousness, it's difficult to make much progress theoretically. This does raise the hypothesis that maybe consciousness has something to do with nonlinearity in quantum mechanics. Hugh Everett proposed in 1957 that there was no collapse of the wave function. Each possible measurement outcome exists, but in different worlds. Measurement causes reality to split into multiple branches of worlds, each corresponding to a different possible result. In a sense, multiple replicas of the observer then exist, one for each world. In each world, the observer believes a different outcome happened. In this approach, an observer can be a machine, with the characteristic that it writes down results. For each possible answer the machine might write down, there's a different world. An alternative version would have the observer have multiple different minds, one for each outcome. In this case, the approach is known as a many minds hypothesis. This approach does not obviously violate any laws of quantum mechanics and claims not to require anything other than linear quantum mechanics to describe everything, including the observer. It has the weakness, though, that for every advocate of this interpretation, in another world, he or she is likely advocating the opposite. So who should we believe? Perhaps instead we should have taken the advice of Willis Lamb, a Nobel Prize winner, who said, and I quote, "I have taught graduate courses in quantum mechanics for over 20 years, and for almost all of them I have dealt with measurement in the following manner. On beginning the lectures, I told the students, you must first learn the rules of calculation in quantum mechanics, and then I will tell you about the theory of measurement and discuss the meaning of the subject. Almost invariably, the time allotted to the course ran out before I had time to fulfill my promise." Unfortunately, it looks like I've run out of time. Thank you, folks.